So I want to go through what we did yesterday, okay? Where yesterday we had you guys look at that simulation. And so if you guys want to, if you want to pull up the lab that you guys were looking at yesterday, if you want to pull up the simulation that you were looking at yesterday, that is absolutely fine. I am going to be talking through kind of the third part. So I'm actually going to pull it up. I closed down all my other tabs because I was trying to see if that would help. So let me pull those up. I apologize for the delay, guys. Happy Tuesday. Happy snow day. Hope you guys had a good opportunity to maybe play in the snow a little bit last night. So I know for us, having a 6-year-old and a 4-year-old, the joy, just the pure joy that first snow that you can play in brings is absolutely awesome. So hopefully you guys, still harness some of that pure joy inside you and could hold on to that a little bit because it's pretty fun. So.
It angers me that we won't ever have a snow day this year, or probably any time in the future, because now teachers know how to use Google Maps.
Yeah, which I wonder, I wonder what they would do, because obviously we still have elementary that are in school. So, I wonder what would a snow day look like? Like my son, they're in Buckeye Valley, and they have a snow day today. They had a 2-hour delay, and then it got converted to a snow day. So,
that's good.
So yeah, I don't know what that would look like. So, but let's do this, guys. I'm going to talk through, and again, hopefully this is just stuff that you're writing down in your notebook. We should have been making Google graphs yesterday, and so here's what I want to talk through. Yesterday, we had 2 objects, each with some certain mass, okay? And what was true was that those objects pulled towards each other with a gravitational force. And actually, I'm going to write this as F capital G, and you'll see why later in the class period. Okay, can you guys, everyone can see what I'm writing on the board, correct?
Yes.
Okay. Now, here's what we know. Newton's third law says that for every action there is an equal and opposite reaction. So what that tells us is that those 2 forces should be the same. Right? They have to have an equal force. So yesterday I asked you guys, if this is the Earth and this is the moon Earth pulls on the moon and the moon pulls on the Earth. And what's true is that those 2 forces are actually exactly the same. Okay? The size of the force is no different, right? The difference is the acceleration. So remember, the forces are the same, but due to Newton's second law, the results are much different. Okay? The mass of the moon is substantially smaller than the mass of the Earth. And because of that, the moon accelerates around the Earth by going in a circular pattern, right? Remember, it's changing its direction all the time. So that's a circular pattern, right? Whereas the Earth really doesn't accelerate. Now, we could talk about, there's actually a center of mass that they actually both move around, but we're not going to focus on that. We're just going to focus on the moon is the thing that is moving, and the Earth is not necessarily moving, okay? Whoopsie, wrong button. So, what you guys did was you moved these masses. I can't move just one. I apologize. But you moved the masses, right? And you changed the mass, and you changed the size of the mass. So let's just start over here. Okay. So, you started with maybe this scenario, and then you went to this scenario. Even though in reality, I guess we kept it the same. We just made it, if this is 1 and 1, and then 1 and 2, and then 1 and 4, right? And what we should have seen, and what did we see here, guys, was we saw that the attractive force, when we did that, increased. Yes? We saw that the attractive force increased when that occurred. Okay, and you guys graphed that and you create a graph of the product of the masses, so M1 times M2 times with the force. Okay, and you created, you should have got a line that looks something like this. Right. Now, this should have been a linear relationship, so y equals mx plus b. And what we're going to talk about is we're going to try to figure out today, what does this slope represent? Okay. So this is stuff that I would be, adding into my notes as we're going through this, guys. Right. But we're going to be looking at, what does this slope actually tell me? Okay. What you later did was you took those objects and you kept them the same mass, 1 and 1 or whatever it was, and then you moved them further apart. And what did we see happen as things moved farther apart?
The force decrease.
Yeah, the force got smaller, right? So if this had a certain force here, then the force got smaller, and then my force gets smaller still. Okay, and you guys graphed that, and we should have had, a distance here and then a force here, and we should have got a graph that looks something like this. Everybody agree with that? So what we can't do with this is we can't use the equation y equals mx plus b, because this is just for a straight line, right? So what we're going to do today, and I don't think we've really done this yet this year, is we're going to linearize this graph. So can you guys pull up your Google Sheets that you guys were sharing yesterday, right? And again, hopefully you guys were sharing it with the group that you were working with, right? Can you pull up this graph? And the first step we're going to do to linearize this, and this is the process of trying to make this graph in some way look like this, or look like a straight line. So what we can do is we can then use this equation, y equals mx plus b, okay? So let me talk us through how we're going to do that. What you had yesterday was you had distance and force, right? And you filled in all that data, right? What I want you guys to do today to linearize this, right? Does anybody know what type of graph this makes? Like what type of relationship do we have here?
Exponential.
Okay. Yeah, an exponential would maybe look more like thinking about like that. But I understand what you're saying. With this, what we can say is like as my distance got bigger, what happened to my force? It got smaller, right? And so that is called an inverse relationship, right? Where the force is more like, we would write it like this. Now, this symbol right here represents proportional. It doesn't equal, right? It represents proportional. It means, this is, and think of this as a fraction, right? As this number on the bottom of a fraction gets bigger, we have 1 over 1, 1 over 2, 1 over 3. What is happening to the value of that fraction? It's getting smaller, right? 1 over 1, 1 over 2, 1 over 3. So what we can do then is look at, let's graph this. So what I want you guys to do is on your Google Sheet, I want you guys to now graph 1 over distance and force. So take your distance data, right? And take your distance data and like in your cell, right? So here's what I would do. If this is distance and this is force, right? What I want you guys to do in this cell here is I want you to say this equals 1 and then divided by, and then this cell right here, like which this cell is maybe A2, right? And you can type in A2, and then that would give me what that value is there. So I'm going to give you guys about 3 minutes. Can we do that? 3 minutes, and then on your Google Sheet that you guys were working on yesterday, I want you to create a graph that is now force on my y-axis and then 1 over distance on my x-axis, okay? I'm not going to break you guys into groups. You're more than welcome to talk to each other, though, about this, but that's what I want us doing now. 3 minutes, go.
Mr. Ellis,
Yeah,
which axis was the 1 over distance supposed to be on?
that should be on my x-axis.
Okay.
So you might have to, if you're just trying to highlight, if you're just trying to highlight the whole thing, if you have like 1 over d here, you could just copy your forces here, because usually Google Sheets will do like x, y, left to right. So if you're trying to just do that, you might just do, x, y, and then it should work out like that. All right, so if we're looking at this, guys, has anybody had a chance to get that done? And what does your graph look like now?
Ours is more linear. It's not still like completely, but it's like flatter and it's going up to the right.
Okay, so now, yeah, your graph now should kind of look like this, yes? Is that similar, Maya?
Yeah.
Awesome. Yep, our graph should look like this now when we do this. Now, this again, like she said, is not linear, right? But what type of graph, Shreya, does this look like?
An exponential.
Absolutely, right? So this is a relationship where, it's similar to an x squared. So now what I want you guys to do, we still need to linearize this, right? It's not linearized yet, right? So what we're going to do is now, instead of, force and 1 over d, let's do force 1 over d squared. So can you guys do that for me? Right? And so now have Google Sheets, take 1 over d. So, if you already have 1 over d, now create 1 over d squared. And we're not squaring this, right? We're squaring 1 over d squared, right? So we're squaring the d, okay? So, your equation could be, a2, or I guess it wouldn't be an asterisk, it would be squared 1 divided by parentheses a2 squared. So that's kind of what I would write into my Google Sheet to find d squared. So this is the process of linearizing, and we'll do this more throughout the year as we work through some a little bit more complicated concepts, guys. But this is a process that the AP loves to ask about, and they love to challenge you on free response questions about the process of collecting data and getting data that isn't linear and then linearizing it in some fashion. Okay, so if we do this, what we get is we actually get a graph that now looks like this. We get a linear graph, right? Y equals mx plus b. And so now we can use that, and what we're going to do is we're going to use that to prove universal gravity and use that to try to understand what does this slope represent in both cases. Everybody cool with that? So if you haven't sketched, can you guys sketch? Make sure you have this graph sketched in your notebook. Because we're going to want that as we are moving through and looking at the idea of universal gravity. And I was just looking at MATLAB. So for those in engineering, right, MATLAB assignment number 3, where you guys were looking at the rocket problem, this is exactly what that problem is addressing, right? And for those that are in my engineering classes, this is exactly what we're going to be talking about in MATLAB assignment 3 that we're going to look at today. Is this idea of universal gravity and how this works. So it's a great timing for us kind of getting this together. So let's put all this together, all right? It's kind of confusing, but I think we can get it. We made 2 graphs. One was force in mass 1 times mass 2, and we got a graph that looked like this, okay? And this one, and then we got a second graph of force of 1 over d squared. And we also got a graph that is linear. right? So I'm going to color coordinate red and blue. And so what we see is here, y equals m x plus b, and y equals m x plus b. All right, so we have two different slopes. Now, if you guys have your data from the Google Sheet, it's definitely something we're going to look at and use today, right? And understand, what do these slopes represent. So I'm going to rewrite these equations as force, the gravitational force, equals this slope times m1 times m2, right? And really it's plus 0, right? This it's essentially should be 0. It's really close, right? So my y-intercept is 0. So we're just going to say this is my equation for the force of gravity. And this is going to be capital G, and you'll see again why, right? On this equation, we have Fg equals, now it's my blue slope times 1 over d squared. Everybody cool with that? So here's what we have to understand. This product of the masses is in this blue slope. And this 1 over r squared is in this red slope, right? And what we're then going to try to figure out is, what is there something else in there? What else is in there that I can understand about this process, okay? So let's do this. Let's keep going. So here's what we're going to say. We're going to say m, the red slope, is equal to some unknown value of a times 1 over d squared. And the blue slope is equal to some unknown value of b times m1 times m2. Everybody okay with that? Now, I don't have values, guys. You guys, if you were to take your values from these two graphs that we made, right, and actually, you know, here's the thing. You kept a constant d, right, here. You kept the masses constant over here, right? What we would see is, we would see that in both of these circumstances, if we were to solve for a and b, we would see that a equals b. Okay? A equals b for us. And so what that means is, there is some other value and some other quantity besides the mass of object 1, the mass of object 2, and the distance between them, right? There's some other quantity that is taking a part in the gravitational force, right? And if we put these two ideas together, we're going to come up with the main equation for universal gravity. And that is this. Oops. That is that the force of gravity between any two objects that have mass, right, is capital G m1 times m2 over, it's, I think on the equation sheet, it's r squared. Yep, it's r squared. This r is just the distance between them. Okay. And so this, essentially A and B, is this capital G, right? With capital G, this is what's called the universal gravitational constant. Capital G is, they want us to use 6.67 times 10 to negative 11 And the units are meters cubed divided by kilograms times seconds squared. Okay. What questions do we have then? So any two objects that have mass are going to be attracted by a force, and that force is dependent upon the size of the two masses, the distance between the two objects, and this universal gravitational constant of capital G. And that's why I call this F capital G, right? It is the force of gravity, but it is, excuse me, universal. It's between any two objects, and that's different than, it's different. That's not an F. Let's try this again. That's different. This is not necessarily the same as this, right? This is the force of gravity when we're on Earth, right? Now, we can use this, and I'm going to show us how this works. But this is of any two objects anywhere, right? You and your computer both have mass, right? That means there isn't a physical attraction between you and the computer, right? However, that is a very, very, very small force because your mass is really small and the computer's mass is really small. And this G which is 6.67 times 10 to the negative 11 is a really, really small number, right? I mean, we're 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 6, right? That's a really small number, okay? So the idea is that these are really, really small forces unless we're talking about a grand scale in terms of, the size of the Earth. Now, the other thing I want to show us is what has to be true is, let's do this. If you are here on Earth, the Earth has a mass. You also have a mass, right? And so there is an attractive force pulling you down. You are also pulling the Earth up, right? And those two forces are the same. Now, there's two ways you can solve it. You can solve it using, Fg, which is just mass times little g, yes? We could also now solve it as Fg equals g, mass of the Earth, mass of the person, over the radial distance. And this is going to be, this is r, right? This is the radial distance of the Earth, right? So the radius of the Earth. Everybody cool with that? Now, I'm going to show you something really cool. And for some reason, when people get to me in AP Physics 2, they're like, my teacher never showed me this. So I want to make sure we get this, right? This is going to solve for your force of gravity correctly. This is also going to solve for your force of gravity correctly. So what that means is that Fg and Fg for a person standing on the surface of the Earth must be exactly the same. Everybody cool with that? So what that means is, let's write this down. Guys, can you write this down for me? That means mass of mg, that means mg must equal g m over r squared. Okay? Now, here's the thing. This is the mass of the person, right? This is the mass of the Earth and mass of the person. This is the radius of the Earth. Okay? What do we see happens in this equation? What can happen in this equation, guys?
Can you cancel out the mass of the person?
Absolutely. And what we're left with is this idea that G is equal to capital G, mass of the Earth, divided by the radius of the Earth squared. Okay? So here's the cool thing. And remember, G is the acceleration of gravity on Earth. Well, what is that? And remember, guys, what's true about, if this is the Earth, what's true about a large boulder and a small pebble? Which one hits the ground first?
Same time.
They hit at the same time. Because the G of both of them is the same. The acceleration of both of them is the same. All right? Which is really cool that this acceleration is not dependent upon anything to do with those two masses. It is dependent upon the mass of the Earth, the radius of the Earth, and this universal constant G. Here's what I want you guys to do. 2-minute pause. Google search mass of the Earth so you need this in kilograms. You need the radius of the Earth in meters. All right? I want you to plug that into this equation. G, you already know what G is, and solve for, you know what capital G is, and I want you to prove to yourself that capital G times the mass of the Earth in kilograms divided by the radius of the Earth squared in meters is 9.8. Go and do that right now. You got 2 minutes, 3 minutes. Get out your calculator, guys. Google search mass of the Earth in kilograms. Google search radius of the Earth in meters. G, 6.67 times 10 to the negative 11. Plug those three numbers into your calculator. Prove to yourself that capital G times the mass of the Earth divided by the radius of the Earth squared is 9.8. I'm going to do it myself. I don't know where my calculator is. Once you're done with that, we're just going to end the class there, okay? Once you've proven to yourself that little g is capital G times the mass of the Earth divided by the radius of the Earth squared, you can log off. We'll see you tomorrow at 9:30. Bam. Very good, Matthew.
Does engineering start today at 12:50?
12:50, baby.
Okay. Are we going to be discussing the MATLAB?
Yep.